Hi, welcome to Module 5. This is Part 3. We left off on the equation, and now we are picking back up with the home heating loss. And the first thing I'm going to show you is one of the ways that we measure home heating loss. It's a good thing to get your home analyzed, or your commercial building, or your industrial building, because heating takes up almost 40%, or cooling when you add together the air condition, 40% of your budget when it comes to electrical energy consumption. So it's about 40% of what you're doing personally. And so it's a very important thing to think of this. And one of the simplest ways to measure is with the old door blower system. And to become a home energy analysis, it's just a simple certification. It takes maybe 2-3 weeks, and then you take a little test, and that's how you get certified in New York. So it's not a very complicated thing. And once again, you're using the equation we just previously saw and a little bit more complex version of that equation, which I'm going to show you in another 2 slides. But the old door blower, so basically you go around, make sure all the windows are shut, all the doors are shut in the home, and then you put your little door blower in the door and you start sucking out the air. And what that does is it creates a vacuum state where anything that is leaking air will start to create little crevices and pull the air in to the home. And you basically go around looking for drafts is what you do. Now, some of the simplest places where you will almost always find a draft is the windows themselves, the framing around windows, the door frame around the doors, sometimes through the changes in interfacing. So stuff like where you go from a concrete material to a wood-bearing material. Those tend to have a lot of air gapping in them. And then air sockets, things like that. Anything with electrical sockets where I had to cut my insulation away from that area, that tends to also be very leaky. And so it's a very simple thing to go around, and you don't even really need a door blow or anything that complicated to figure this out. You know that these places are going to be leaking. If you can see light under your door frame, then air can get through. Air molecules are incredibly tiny. Little tiny slivers and holes are the size of the Grand Canyon to air molecules. So they have no problem slipping into your home. And so you will get air exchange through those places. The newest and best technology that's out there now to analyze any type of energy loss, and if you had a commercial building, you would definitely want to do it this way, and that is through utilizing something like a handheld thermal imaging camera. And so this is the really simple Flurry i5, which gives you a little point and click gun, and then there's more complicated versions. I myself have a more complicated box style, which is a 2-hander that I can hold kind of like frame style and hold up and do a screening of the home. But even right in this image, so the areas where you see the red is where the heat's really leaking through, and where you see the white, it's just basically sharing complete exchange. And so these windows are completely exchanging heat energy, right? This backsiding door is doing a lot of heat exchange. You can see here that there's a lot of heat exchange in these locations here. This area where you can see this heat exchange, those are probably dampers in the roof that's creating these heat exchange. So that's quite purposeful. But this one here is an interface change. So that's because there's no insulation between the interface change of the roofing and the siding, and so the heat is just sliding right through on that set. Sometimes where we see it, it's not that there's a heat exchange, but there's actually damage, or there's no insulation at all, and that has potential in this spot right here. So that's an interface change where the roofing's coming down, but it could also be damage, and it could be water damage, which is another interesting thing that I'll point out. Sometimes when you see a lot of exchange of heat energy, it's actually water damage within the building. And so when I would open up a wall inside, I would find a lot of water damage in that interface. So I would say there might be an issue with the siding material and the roof slope in that location, or it's something that I would look into when I see something like that. So it's something to think about, and this is our standard energy analysis. And once you get in the swing of working with something like this imaging, you get really used to what you're seeing, and you can kind of call what you're looking at. So measurements for home heating loss, obviously there's places where you're going to have a lot of loss, and this is the same image as the black and white, just showing you this variation between home heating loss. Obviously, the reasons for doing this are plentiful, but the four main ones that the book likes to give you is to reduce leaking of air, avoid moisture and condensation problems, uncomfortable drafting, and cold so that you can use your indoor and outdoor spaces, and making sure the home air quality is not contaminated, which is another big thing. So we make these buildings so airtight that now we're starting to create polluted indoor air quality issues with things like we bring in our couches covered in flame retardant materials and things like that, and then we're breathing those in. And so you think a new car smell, that new car smell is actually a whole concoction of chemical compounds that you're breathing in. And so people who have high risk of toxins and those high toxicities or have diseases that put them at high risk of toxicity, now the new thing is we're making these airtight homes. Now we're purposely ventilating them. So there is a balance. You have to create that nice exchange and do what's best for you. And obviously the inexpensive thing to do before you go running off to buy yourself some windows to fix all your woes in this world, please think about doing the really simple fixes, the inexpensive ones first. Now, storm windows is the first one listed, but before you ever go for storm windows, make sure that you have insulation in your walls, that you are weather stripping, and that you are caulking material on there. And then this is the book's little retrofit of home energy conversion things to do. We can determine how much energy is being lost over the course of the year without having to take the equation that you saw in the previous slides, and instead of using change in temperature, we're going to switch that out for a different specific part of the equation, and that is going to be switched out for a degree day. Now, the degree day is something that you may have seen at the back of a seed packet, so it works there too. And basically what it is it's taking into account all of the degree in days per year in degrees Fahrenheit, and it's creating a number. Now, if you live in a specific location, you're going to do home energy analysis. We have degrees day down to regions. And so if you're coastline, you're going to be slightly warmer than interior. And so these numbers, while they're nice and clean and this lovely image, and for the sake of this course, you're going to be using big numbers. If you ever go into the subject matter professionally, these numbers are going to be 4,456. Like they'll be very specific for your region and location. It's something that you would look up on the chart. The numbers are done for you, and then you would insert them into your equation. And so here is the equation. So we're going to find Q total because you're going to be finding the number for the year. And that is equal to the sum of all your 1R values times their areas, which means that I would take the 1R value of the area of each and every window and add them together. And I would take the 1R value of the area of all of the surfaces that happen to be my exterior, sheetrock, insulation, plasticine board, every material that's there. That would then get added together. And so I would take the sum of everything that makes out the exterior surfaces of my home, anything that touches the outside world. That would become my sum for this area of the number. I would then times that by 24 hours in the day. That'll cross out hours from my equation in R value. And that will get times by my degree day, which is something that I would look up based on region off my table. So the example that we give down here is calculate the difference between a storm window and a single pane window, and they give you this lovely number. And then they ask you for the average cost of energy. Now, this exact question is something that I repeat already for you in my walkthrough video, my math walkthrough video. So I'm going to jump to my next set of imaging slides and finish up this little prep and just show you another equation. You need to be able to do these equations. If a lot of you are having issues, I can build more math walkthroughs, but I did already build one, and so I would like you to take a look at that before I jump to it. Quickly, as a topic overview of what we just covered, is you should be able to determine conductivity of heat loss in a short term. So that's my QC over time. You should know that R value units are feet squared, hours, degrees Fahrenheit, BTUs. Measurement of heat loss creates gas exchange and thermal imaging. You determine conductivity of heat loss based on long term. And that there is a Q total for the year, which is the sum of all R values times their areas, times 24 hours in a day, times a degree day. So on that note, I'm going to have you look at the math videos, and I will also create a walkthrough of question 17 because it's complicated.